Yeah.
Just two main things to talk about today. One was the thing we were talking about, that table
Yeah.
of remaining stuff. Wait, I have it here. So it's this thing. And the key thing about these compounds, some of which you have and some of which Yuhang's going to send more sample for, is that it's the set of the originals with the alcohols, and then it's the set of the amino versions plus derivatives of those. So we're changing the OH to the NH2. And then it's the guanidinium versions of those amines. And then lastly, some miscellaneous extras, right, which are of interest for various reasons. But the key, I mean, for the paper, the thing that we've got to have is the sense of potency. So for example, with this compound, we don't have anything. And for these two guanidinium ones, which are coming, it's the sort of full set of the IC50 and the KI.
Okay.
Yeah.
And then I guess for any compound, and we got it for all these, for any compounds which look okay, then the MICs were interesting, right? So for the guanidiniums, for example, they are registering some activity. We're interested in seeing, what these two compounds are looking like.
Yep.
And then if they're no good, then of course, there's no point in doing the MICs. But if they are showing something, then the point about these compounds is to see if they could accumulate better. So we're measuring the accumulation. Well, not we, but Callum in the crypt mentioned measuring the accumulation for all of these compounds, and that's what Yuhang's preparing the whole set for. But for but in addition, right, we want to see if any actually give a MIC.
Okay. Can I make a suggestion? So
Yeah.
where you do see accumulation, one thing we could potentially do is, because we do this with other antibiotics, we basically use accumulation assays of precursors. So, for example, if there is any activity in the cell of the compound, we would expect to see an increase in the concentrations of UDP-MURNAC, the substrate, and in concentrations of UDP-MURNAC-ALA, the product. So we have looked at precursor pools before in other contexts. I mean, you think this is something worth pursuing?
I guess if we see, well, I guess it depends what the accumulation data says, doesn't it?
Yeah.
It could be an additional data point for sure if we get that. Yeah. So, well, I mean, we'll know that, in early March, I guess, when Yuhang's managed to deliver the compounds to the crick, and we will have, and Callum would have had time to run the assay because it's fairly quick. So I guess we'll know then before the next meeting, maybe. Yeah. But I mean, I guess the primary thing is to get these guys, particularly with the guanidiniums, when they are fresh, right? So when they arrive, to try to measure them when they are reasonably fresh, just to make sure that they don't degrade in any way, because we're not very used to handling these compounds, honestly.
Yeah.
Well, I mean, all of the stuff that we've been sent the past year, or more actually, has been assayed within a month of receipt, and they've all been kept to -80 before use.
Yeah, that's perfect. Yeah.
And thawed momentarily and then quickly back to the -80.
Yeah.
Yeah.
Okay.
Yeah.
I mean, what worries you about their stability in particular?
Nothing in particular, just that we're not used to them, right? So we don't know. And we haven't got a lot of experience of making them and then repeat analyzing them after a while. So we haven't really got a good sense of their chemical stability. That's all.
Well, we can make, as we've done this before as well, make a working stock as well. So we don't keep freezing and thawing the original stock. And if there are any issues, we can always go back to something that is fresher, that hasn't been thawed multiple times. So we can do the same as well. Yeah.
I mean, potentially just measure the mass, do a mass spectrum here of them.
Yeah, I mean, it's something, Yuhang, you might want to think about doing here if you've got a sample of an NMR or something, and then you just, wait a week and then take it again and just to check what it's like.
Or like doing 2-3 cycles of freeze thawing or something like that as well.
Actually, I do have accidentally done this before. One of my the WYH9 actually. There are some stocks that I got was digged out from my old NMR samples. I just repurified the DMSO stock.
Right.
Yeah, and then I do high-res mass spec and NMR out of it to make sure it's pure. But normally,
I guess we want to be more careful with the 180 newtons one, right?
Yeah.
Yeah,
Well, just because we don't really know.
Yeah, the guanidiniums,
And these guys here, you know, we were looking back at the data the other day. I mean, they're not actually that bad in terms of comparison with the other samples that we've seen. And so
we got MIC data for those. So we might have more things than on the table already. But yeah,
okay.
I will send that to Jenny and Colette so they can fill it up.
Right. All right. Magic.
Yeah, thanks. Thank you.
All right. And then, of course, the other big thing was the structure.
Yeah.
Do you want to?
Should I share first some binding stuff that I've done?
Oh, great. Yeah.
And then, all right. Here. Can you see another presentation?
Yep.
Okay. So I've done some SPR with the WYH compounds. I can't remember if it's YH or HY every time.
Yeah, it's so good.
Anyway, so I've done some ADPCP as a control, and then all these compounds against MUR-C, MUR-D, and MUR-E. I managed to not have to immobilize the protein permanently. For Pseudomonas, they bind better to the sensor, so I can do that. But if we look at the ADPCP, MUR-D might have some issues in terms of stability inside this chip. So we just need to keep that in mind. And I've got some KDs for these compounds for 77 with MUR-C. That one was given very weird signal. I think there's something was going on the sensor with this compound. So I don't fully trust this data on the 77. And then I know they look a little bit disordered, but it's because 78 was having a little bit more of a K-off. The K-off is a little bit longer. So I didn't want to have any interactions of the compound 78 with any of the rest of the experiments. So I left it for the end in case there was some stickiness of the compound. And yes, so we've got relatively high KDs, they're quite high, which would explain why the crystallography has been so challenging with these compounds, because for crystallography, you want good KDs more than in inhibition. Now the curves vary a bit. So I put here the curves for 9 compound 9, 25, and 78, which, if I'm not wrong, these are the ones that we got structures for. 25 was a little bit messy because 25 is not very stable at high concentrations. So this was 500 micromolar, and it was already starting to precipitate over time. So I got it into solution, but obviously by the time it got to 25, which is at the middle of the run, so that's 8 hours. So after 8 hours in the instrument, it already started to precipitate a bit. So the fitting is not great. Then for 9 is a little bit better, and 78 is all right. Yeah, so they all look like that. Everything looks okay, and nice on the data. Some of the compounds give a negative binding, which we have observed in the past. This negative binding is specific to the protein, so it's nothing to do with the surface of the sensor, but indicates that there is either large conformational state, or maybe we've got more than one multiple binding sites that I cannot discriminate, but something large is happening on those. And it was more permanent on MUR-D and MUR-E on the bindings.
What's the significance of the different colors on the points?
Oh, these are different concentrations. They're just colored by different. Yeah.
All right.
There's no significance.
It's 76.
Program. Sorry, second.
76, which has the 3 micromolar against MUR-C. That's one of the guanidinium compounds. It's interesting.
Yeah, the 76. We also got another 13. So I might actually go back and try to get some structures, for example, for that one, for 76.
Yeah.
and see if that's because if we look at 25, we are talking about 100 micromolar. And yeah, and the rest is just 20s, these ones. But we got the structure with 78, right? But with 78, the thing is that the K-off is a little bit slower. So I think we managed to get the structure because it stays longer bound to the protein. So I think that's why we got it. Also, we need to keep in mind that this is an immobilized protein, and we don't know how good the correlation is. And I don't think it is very good from what I'm going to show you next. So this is 25. Let's remember 96 as the KD for Mercy. Now, there was a demonstration for this new technique. I don't know if you heard about it. The FIDA-Bio is a flow-induced dispersion analysis, and it looks at the dispersion basically on a capillary. So if you got a larger particle, then the dispersion is a little bit broader. And then it also has, it can also measure the fluorescence intensity as well. So you can look at the binding of the compounds by the fluorescence intensity of either a label that you used or your tryptophan fluorescence. So I found out the day before they came that this demo was happening. So I decided to ask for a spot, and they gave me one on the last day. So we could do a couple of experiments, right? From these experiments, you can also look at the potentially, I need to read more about this and know more about this, but there's not a lot of information on the website, so I need to talk to the rep. But they can also calculate the radius of the particles that are on the liquid. I guess is related to the dispersion of the flow. So we looked at the radius and we look at the tryptophan fluorescence in the presence of WYH25, right? So this is the fluorescence intensity. So we got some binding, and we've got KDs of 4 micromolar, which is very different from the SBR, right? And then they called the compound SM25 because I only gave them the number 25. I didn't want to give them more. And then the next one, this is the profile in 2 different ways of setting the experiment. The red one is one, the green one is another one. But anyway, basically saying with increasing concentration of the compound, we are having an increased size of the protein, which could be because the protein is being a bit unfolded and having a lot of different conformations, and we just have a mixture of different conformations of the Mur Ligases. And then the more you increase, the system gets saturated, and then you've got a more compressed conformation of all the molecules, right? Now, all the crystallization that has been done is with 1 to 3 and 1 to 5 molar radius. This is because the compound starts to crash. So I couldn't go higher than 1 to 5 or 1 to 3 molar radius, which means we are about in here, just where everything seems to be very flexible and very a mixture of stuff. Yeah. This is for 25, okay? But we don't know what happens with every single compound, but yeah. So another idea that I thought is just trying to see if any of the compounds will go to a really high concentration and see what happens on the crystallization, and if we can get something. Because if this means that we are having a mixture, obviously we're not going to be able to crystallize something that is a mixture of different conformations. So this is quite interesting. And now I want to follow up on this. So I talked to FIDA-Bio. We are trying to organize another demo in Madrid. So we can, I want to ask them for 2 weeks because there's a lot of things I want to try. And then we can screen all the compounds, the W compounds, and see what are the differences. And then I can do proper experiments with the crystallography. Yeah, which, it would be very interesting. And this looks more reasonable in comparison with our nanomolar affinities, IC50s. Yeah. This looks more in correlation with that than the data that we got from the SPR. So actually, these Mur Ligases might not be the best protein for SPR analysis. Then, as you know, we got the structure of the full-length Pseudomonas Mercy. I put here some details of how the experiment was set up. The solution is at 2.3 angstroms, which is quite reasonable. We've got 2 molecules in that symmetric unit. And yeah, the binding here, and the compounds are really nice. I can show you later the density if you want. And then I'll go back to that later. We can show you the structure. Right. So we've got here the compound. I guess you have looked at the structure already.
Yeah.
We got some interactions, hydrophobic interactions with these loops, which this region is the one on the right is the one that is missing on the other structure. So if we overlay with that ones that, I think this is the WYH9. Yeah, the right side is missing on those structures, right? And there is another thing to mention. I put a magnesium there in the structure, but it could be another ion. I need to identify that later once I further in the refinement, because there's a lot of things that I need to fit. There's a lot of blobs that I need to find out what they are. And then there is also something that looks like a small molecule of ethylene glycol, which makes sense from the condition. And I think this is just a consequence of the pocket. So because if we look at the surface, right, if we look at the surface there, you can see here the ion, and then this one there at the back of the pocket, which is actually the opening that goes to the substrate side, basically. So the substrate will be binding here. And we have here 2 very nice pockets that could fit something. So if you wanted to make more compounds, you could expand that way, although we might end up making the compounds less specific for the other Mur ligases because that's the substrate side. Height, surface. Right, and then I've been comparing them with the 2 structures that we got. Right. But I'm not sure how to compare them properly without this section of the protein, right? Because these regions of the compounds are more flexible than the rest of the compound. And actually on that one, the flexibility is quite great. And looking at the maps, electronic maps, is also low occupancy as well on this region. So these could actually be flipped and it could be closer to this alpha helix. And we don't know what's the likelihood of that to happen. So I'm not sure how many more conclusions we can make of this comparison because we're lacking that section. So still we need to try to find those structures, or, which is coming back here, those structures, or maybe also try some NMR. So I've been in Madrid a few weeks ago. I was doing some exams to get a permanent position there. And the last exam was about the research proposal. So I presented the Mur ligases, but I only presented the TB Mur ligases. We recently got some structures, and I was mentioning that with other Mur ligases, we had issues with the structures. So yeah, we just need to be careful with that. Right, and then after that, there were a lot of people that came back to talk to me, right? And a lot of people were NMR people. And they said that they will love to try the system with our compounds and our protein and see if they can identify the binding partners of, well, the residues that will be binding the compounds, which might be a way to go when we don't have structures. So if we do NMR and we see, for example, for 9, that these interactions with this helix are non-existent, then we don't have to worry to create a new structure with that one. We could trust this structure more, for example. That's what I was thinking. And in the meantime, obviously, just trying to get the structures of these 2 at least. Right. And yeah, because if we get 25, imagine, and we see exactly the same structure, then we have more confidence that everything we have done in the past is good. Yeah. That's what, my conclusion of the whole thing.
For the helix, the new helix, is it making any, productive binding interactions with the compound, or is it just sitting there?
So it looks like it's helping to get the hydrophobic interactions, but I need to do the proper interaction analysis and look at all the sizes. Because it might just be the environment that is creating. I don't know if without that LX, will this be that flat or will it be a little bit more to the left? Show surface. Yeah, so it's just getting the surface quite nicely. And then on these structures, you've got a symmetric unit on the opposite side. So it could also be, these positions could also be influenced by that. And it's other residues, it doesn't look like this, the pocket.
Is that lysine?
Right.
This one is, let me show you. Yes, lysine.
Is that close enough to have any impact at all on binding or orientation of the molecule?
In this, it might have some interaction, but it's a flexible residue, so we don't know really what's there. We will need to do more experiments, and an NMR experiment maybe might tell us a bit more.
Yeah. Because we did talk about playing around with pH before, didn't we? And IC50s and things like that.
Yeah. That's another thing. This is done with pH 6.5 as well.
Yeah.
Right. So with the, I mean, that structure does kind of confirm that the variable unit that's hanging off the core. So in this case, it's the, the purple cyclohexane and blah, blah, blah.
Yeah.
That whole region does tolerate quite a bit of change in terms of the IC50s we've been seeing. And before the full length structure, we didn't have anything there, and we just assumed that it was pointing towards solvent, and so it could tolerate variation. I guess it's interesting to see that the helix is indeed there, and there's still obviously a channel out, right? If you look at the bigger structure, which can accommodate these changes. So the one that gave a good result on the SPR, it has the cyclohexane, but it's essentially para substituted. So quite rigid actually in where it can point. And this structure does confirm, I think, that there is space there for that.
Yes. Yeah, definitely. Like it's a good pocket for expanding and making more compounds. There is a space for more. There's plenty of space for more. Show a surface, please. Yeah, there's plenty of space for more.
Coming towards us.
Coming towards us, and into here, for example, we've got charges that we could try to get a hydrogen bond in there. You hear more hydrophobic interactions if you wanted to go that direction. Yeah, and then obviously you also have the other side as well, which is a little bit more tight, but you might be able to expand as well on that section. Yeah.
Is there any possibility that because the truncated parts was very was the flexible part, was the flexible domain, so it opens and closes. So when the parts that we are making change in the molecule being replaced with different side chains, the entire protein could actually accommodate and bring up the induced fit to make the compound staying where they is. Is that possible?
It could be, but we have also observed these conformational change when there was only substrate bound, for example, for Mur D. So it could be there's more than just one binding event for that to come down. So I don't know how much it will accommodate, but I think it can accommodate a lot. Yeah, like a lot more than initially thought. Yeah.
Can you just go back to the other pocket a second, just to show that the sort of the substrate pocket?
Right. So here. So the substrate will be here.
Right.
I've got like the substrate. You see, it will be sitting around there.
Yeah. Right. So the the CC4 carb plan is to build off that ring in that direction.
There is space,
yeah, and the idea is to pick up interactions with the alpha helix that's up in that region.
Yeah, that will be good.
I can't quite see that helix on this view, but it's there, right? This is as expected, so it's the same.
Yeah,
as
this is the helix.
there it is.
Yeah, the
It's
helix
exactly here.
is really long, like is the whole pocket length basically.
Right.
So it
Oh, I
just goes
see.
along the pocket, and
Right.
and as you can see, like these are from other structures, these phosphates. So this region, this side of the pocket, is actually quite nice to try to bind the stuff to it.
Yeah.
So yeah, so if you want to
Mm.
spend towards that direction, I think it's a good idea, especially now, and we know there is a ethylene glycol there, some more ions. Yeah, it has potential, I think.
Right.
Mm.
Good. I didn't realize it was the same helix.
Yes.
Okay. So okay. Great. Yeah. Good. That's great. Glad there's no change there. Okay.
So, yeah, it's quite nice.
Yeah. Really good. So those are the two directions. That's fine. I mean, with the full set of IC50s, right? We will be able to say something nice about why we see what we see. I'm still confused by the compound that. So for the AZ595, the core compound, if you chop off that, the side chain, which is pointing in the first pocket, and you just replace that with an NH2. So that's a compound that Yuhang's made. And it doesn't do very well, but I still don't really get that because it's a small chain. So the implication of that compound is that it helps to have something there. But it's quite a dramatic impact on the potency, and I guess I guess there must be an interaction of some kind that we're
We
losing.
could do some more analysis. We could ask Phil Stanfield and see if he can see any differences when doing docking and molecular dynamics.
Oh, you've got somebody who could do that, do you?
Yes, we are collaborating with him as well, so we can ask them if they have got some time. If not, in the worst case scenario, we'll just wait until March until the student comes, and then she can do it with them.
Right. Because I mean, it would be great to say something sensible about that now that we've got the structure. It's really good. Amazing. You must be very happy with that.
Oh yeah, he's a bit relieved that we can actually get something, get the structure. But but I think even though we got it, I think we should maybe think on other options, like for example, the enema, which is something we discussed already in the past.
Right.
But I just thought, like, with the hype of people being interested, and it might be the moment. Yeah.
I mean, I suppose the other thing is, given that these are basically mimetics of the co-crystals of the structure with ATP, given that this is where the pocket that these compounds bind in, and given the auto mechanism of the enzymes, then it will probably be I'm not going to say straightforward. I'll never say that, but it's quite plausible that you would get a co-crystal structure with the UDP substrate in the presence of these compounds. Which would be worth doing, because of course that's actually perhaps the main species that you would expect to see in assays where you actually see large amounts of inhibition by these compounds.
Right.
Yeah, that could be another option.
Yeah.
Oh, I know what I wanted to show you there. Is it opened? Yes, should be opened because I was working on it before. Right, this is a compound and the density, which is quite nice all over.
Right.
Yeah,
Amazing.
it has a good coverage, and then the B factors are quite decent as well. We got some nice interactions, and it's in both the units is the same. It's quite nice. Yep.
Wow. Yeah, that's great.
Yeah.
Yes. Yeah. Okay. And the NMR you're talking about is to show protein substrate interaction. That's the idea, is it?
Yeah. Protein inhibitor interactions.
Yeah.
Just to see which residues are the ones that are interacting, because that could guide as well the modeling as well if we wanted to get a real 3D structure.
Right.
And then at least we can also compare that with the structure that we've got. If 25 is not binding to any of the residues or doesn't really have any interactions with the residues in the alpha helix, then the original structure is valid, I think. The same for the other one, for 9. It's just to make sure we can use everything that we can. And then if we don't get any more structures, that at least we got some information on how they bind.
Right.
Yeah. And I have a last slide. This is my email. In 2 weeks, probably my current email will disappear.
Oh, wow.
So, but I don't have one for Madrid yet. They are setting it up at the moment. So yeah, that's the one that you can use for everything.
Okay. Okay, will do. Yeah, great. So are you taking like samples of compounds over?
Yeah.
Okay.
I'll bring some compounds with me, proteins obviously, so I don't need to purify, and I can start doing stuff as soon as I arrive. Yeah, I'll bring stuff with me. Okay.
If Yuhang sends compounds to Warwick, will you be able to get them?
Yeah, they should be able to send them. Yeah.
Okay.
Yeah. Right. The new compounds, whatever binds, if they're nice, then they can send them to me.
Yeah. Okay. All right. Great. All right. Fantastic. Was there the one that I mentioned this last time about the possibility of doing this ASMS screen, the new kind of ASMS screen, right?
I emailed them a couple of times, but they haven't replied because I submitted the things, but I haven't gotten any email confirming that the submission was done. Yeah, so I don't know. Maybe it didn't work. The submission didn't work.
Yeah.
Yeah, but I've got the proteins ready to ship. I've got them ready to ship.
Okay, let me chase that because it made you swamped.
Also, because I had issue with my email. I don't know if they have replied recently, and I just haven't been able to see it.
Okay, great. I'll chase that. Perfect.
Thank you. Yeah.
All right, sounds really good. Amazing.
No problem.
I think that's all the updates that we had, and I guess it's all the updates you have. So we are, yeah. I mean, so by next time, I guess we'll have made some more progress towards this paper that I think we all need to get out to demonstrate what we've been doing all this time. I mean, it's a slow burn, but it's important work, really.
And as soon as I get to Madrid, I think I'm gonna talk to the NMR people and see if they can run anything. Because the faster, the sooner we do it, the better. And then at the beginning, I'm not gonna be able to start working on day 1. But if at least I've got the protein and I got the compounds, they could start doing something.
Right. Yeah.
We are not moving forward.
Also, we had this. We I don't know if you know about this project in the group. We made up a 96-well plate of random assortment of compounds from the group, from everyone's different projects, and we're writing a paper about the importance of cross-screening and trying to convince people to make up plates of compounds and send them out for screening and collect the open data and all this kind of thing. We've had it screened by the UK HSA people at Porton Down against a few things, and we've got some interesting data coming from that. There is one compound in there, one of Guy's compounds, that seemed to do something interesting in one of the antibacterial assays that they ran. So I'm just getting the data back for that. I think it was intended as a Mur Ligase inhibitor. I think it's from one of those series. So we're getting the data. I just asked for it the other day because I went to see them last week, and we'll find out what the compound is, and then we can have another look at it. But there's something in there.
That's great.
Yeah.
Ooh. Okay. Things are starting to move.
Yeah.
Hopefully.
So are you planning to do any more progression towards TB Mur Ligase inhibitors?
Well, we'd love to. The issue is that Guy got this job at the Crick, and so because it was a permanent job, he gave up the end of his fellowship, so he would otherwise have carried on until like October. But he had to give it up to take the job up. So he won't really have much time to progress that. But if we do see promising data for the TB compounds that he's interested in, because he was doing 2 different projects, then there are ways in which he might be able to do some work on those at the Crick if he has an interested PI. otherwise not, because he's now going to be busy with a bunch of other projects at the Crick. So, so we've still got some molecules being evaluated in a phenotypic assay in the Crick, and trying to get some compounds screened by the Institut Pasteur in Korea. We're just waiting on contract being sorted out. And we've had this screen done at Porton Down. So, you know, if anything pops up there, then there may be a way we could try and progress it. Yeah.
Okay.
Obviously, we'd like to.
Yeah.
No.
Good, great.
All right. Fantastic. Nice to see you.
Yeah,
too.
same.
Be in touch soon.
Yes. Take care.
Take care.
Later.
Bye-bye.
Bye.
Bye.
Bye.